Hello students, in this video we are going to discuss about basics required for understanding the lesson electrostatics. The very fundamental thing to start with is electric charge. The symbol used for representing electric charge is Q. Okay. Now take a look at an atom. So you all have an idea about an atom. An atom consists of protons, neutrons and electrons, isn't it? So the this nucleus contains protons and neutrons. And around this nucleus, there are electrons revolving, isn't it? So what type of charge is possessed by these protons, neutrons and electrons? You know that protons possess positive charge, electrons possess negative charge and neutrons no charge at all, isn't it? So we'll come to the meaning of charge first of all. What is the meaning of charge? Let us look at charge and its properties. Charge is a property associated with matter. Let us look at this point carefully. Charge is a property associated with matter. Matter means what? Matter means what? Mass. Okay. Without mass, there is no charge. No mass, no charge. Means what? Suppose if you look at electron has negative charge, proton has positive charge, isn't it? And electron has some mass. Electron has some mass, proton also has some mass. So this charge, negative or positive, this charge doesn't exist without mass. That is the first point we have to remember. Means what? There is no charge without mass. What is the next point? Charge is a property associated with matter due to which it produces and experiences electrical and magnetic effects. Suppose here I have a negative charge, means suppose example electron. Okay, if I place an electron over here, what will happen now? Here I have a positive charge and here I have a negative charge. You know already, unlike charges, they attract, isn't it? So this will come near this proton. Okay, if I place a proton here or any positive charge here near its field, now what will happen? Now these two charges will repel each other. Here if I place electron, it is getting attracted. If I place proton over here, it will be repelled. You know that point already. Like charges repel each other, unlike charges attract each other, isn't it? So these properties of repulsion and attraction is only possible because of the property of the matter called charge, isn't it? Only because of the property called charge, these things are possible. All these electrical effects, attraction, repulsion between the charges, isn't it? Now, continuation. Due to this we have discussed already. Magnetic effects we will discuss in the further lectures. Okay. Next point. Every atom is electrically neutral, containing as many electrons as the number of protons in the nucleus. Okay. So anyhow, our neutrons are having no charge at all, so we need not to bother about them. Here, charged particles are only protons and electrons, isn't it? Now let us count the number of protons. Here in the nucleus there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons are there. And around this nucleus there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons are there. Means as many protons are there, those many electrons are there, isn't it? That means how many positive charges are there? There are same number of negative charges are there. That means it is electrically neutral. Suppose 10 protons are there and 10 electrons are there. So it is electrically neutral, isn't it? No charge at all. For an atom, there is no charge at all. That is what meant by an atom is electrically neutral. Moving on to next slide. The third point. If an atom loses electrons, it becomes positively charged. So take a look at this atom again. If suppose I remove this electron from the atom, then there are 10 protons and only 9 electrons, because I have removed one already. There are 10 protons and there are 9 electrons. That means what? Positive charge is dominating the negative charge. That means if an atom loses electron, it becomes positively charged. Got the point? Whenever electron is removed from the atom, it becomes positively charged because positive charges are dominating here. The same way, if I add one electron to the atom, it becomes negatively charged, isn't it? Now what I'm going to do now? I'm going to add. Now I'm going to add one electron to this atom. Now what will happen? There are 10 number of protons, and when I add one more electron, there are 11 number of electrons. So which is dominant now? The negative charge is dominant. So the atom becomes negatively charged particle, isn't it? Now, when a body becomes negatively charged, its mass slightly increases because the added electrons have some mass, isn't it? Electrons, even though they are very small, they have some mass, which is one electron's mass is 9.11 into 10 power minus 31 kgs. Even though it is very very small, when it is added to the atom, atom's mass increase or not? Atom's mass will increase, if not significantly, but to a minor extent it will increase, isn't it? The same way, when a body becomes positively charged, its mass slightly decreases because of removal of electrons, isn't it? To make a body positively charged, what we have to do? We have to remove the electrons. If you remove the electrons, the body becomes positively charged. But when we remove the electron, we are removing the mass also. So its mass decreases. Here, when body becomes negatively charged, we are adding the electron, means we are adding the mass. So the mass will increase slightly, isn't it? Now, next point to look at is this one we know already. Like charges repel each other, unlike charges attract each other. If you place two protons next to each other, they will repel. And if you place one proton and electron, they will attract each other. This is one more property of the charge. Next, charge is transferable. Look at this point very carefully. The charge is transferable. Here I have two bodies A and B. The body A is negatively charged. The body A is negatively charged. Now the body is initially neutral. Initially it is neutral. Now look here, there is no contact. Between these two, there is no contact. The second diagram you can see, they both came into contact. Now what is going to happen? The body A will transfer some of its charge to the body B. Because of the contact here, the body A will transfer some charge to the body B. Okay. You can see that now. Earlier A had total 3, 6, 9, 12 charges. Earlier A had 12 charges. Now A is transferring the charges to the B slowly. Now after complete transferring, A is left with 6 charges and B is left with 6 charges. This transfer of charge will take place until equilibrium is attained. Now A has 6 charges, B has 6 charges. Now they are separated. When they are separated, A will be left with 6 charges and B will be left with 6 charges. Okay. So this is how the charge can be transferred. Okay. Next point. Charge is always associated with mass. This we have discussed already. Now, the main important point is charge is conserved. Charge is conserved. Conserved means what generally? To remain same, isn't it? Conserved means to remain same. Now here suppose I have a body with 4 electrons. Means it is a charged body. It is a charged body. It has 4 electrons initially. And the second body, which is a spherical body, has no charge at all. But when I bring this in contact with the spherical body, what is going to happen now? Its two electrons from this body will be transferred to the spherical body. 2 electrons from here will transfer to here. Now, what is the total charge? What is the net charge initially? The initial net charge is 4 electrons. Here, after transferring also, the net charge is how much? Net charge equal to 2 electrons over here and 2 electrons over here. Again, it is 4 electrons only. That means the total charge will remain same. Even after transferring takes place, the total charge remain same. That is what meant by charge is conserved. Now, next property of charge is invariance of charge. So, let us compare the charge with mass now. We know that mass changes when it is moving. Mass changes when it is moving. That can be understood by this equation. M is equal to m naught upon 1 root over minus 1 minus v square by c square. This change in the mass is not observed in the regular day-to-day life, but whenever the mass moves with a speed almost equal to speed of light, then the mass of the body changes. Okay. So whenever the body is at rest, the mass is called rest mass. The mass is called rest mass. But whenever the body is moving, the mass of the body changes. We can see this equation. The moving mass is equal to rest mass upon root over 1 minus v square by c square. That means whenever this v increases significantly, then the mass changes. That means mass depends on velocity. But coming to the charge, in case of charge, it is not like that. Even though a charge is moving swiftly, very fast, still the charge doesn't change. There is a difference between mass and charge. Mass changes with velocity, but charge doesn't change with velocity. So how can you verify that? How can you verify that the charge doesn't change with velocity is, take a look at this atom again. Here we know that electrons inside the atom, they move very fast, isn't it? They move very swiftly. They move faster than protons. Protons are confined to nucleus only. They don't move that much faster when compared to the electrons. Electrons move very faster. If charge depends on the velocity, then the neutrality of an atom would be violated. What does it mean? The electrons are moving very faster when compared to velocity of the protons, isn't it? So, if charge of a particle depends on the velocity, these electrons should have more charge compared to protons, isn't it? But here, atom is neutral. Atom is neutral means the total charge of these electrons is equal to the total charge of these protons. Then only atom is neutral. If electrons are moving faster and charge is more, means the neutrality of the atom is violated, isn't it? That's why we can prove that the charge doesn't depend on the velocity of the moving particle. Okay, next. Now coming to units of this charge. We know that already current is equal to current I. The symbol I stands for what? Current. Current is rate of change of charge. So I equal to dq by dt. So here q is what? Change in charge upon time. Okay, so dq is equal to I times of dt. Here dq is a small charge or elemental charge. I is current, dt is a time. So what are the units for charge we can write? For current it is ampere and for time it is seconds. So total we can write the unit for charge is ampere second. Ampere second. That is S unit of charge is ampere second. Where 1 ampere second is 1 coulomb. Coulomb is a scientist name. 1 ampere second is 1 coulomb. And coming to CGS unit is ESU. It stands for electrostatic units. CGS unit is ESU, stands for electrostatic unit. Or we can call this stat coulomb, where 1 coulomb is equal to 3 into 10 power 9 electrostatic units. Okay, these are all the basics you have to remember. Now coming to dimensional formula of charge. We have seen already the formula for current is Q into T. That is charge into, Q by T. Now Q is equal to I into T. I times t. Okay. Now for I the dimension is a, that is ampere. For time the dimension is t, that is time in seconds. Okay. So the dimension formula for charge is this. Now take a look at this note point. Charge given to a conductor always resides on its outer surface. Now here I have taken a solid sphere. Solid sphere means inside also it is filled with some mass. Hollow sphere. I have taken hollow sphere here. Be it any body, the charge always resides on its outer surface. It doesn't stay inside. It always prefers to stay on the outer surface of the given body. Be it a solid sphere, be it a hollow sphere, be it any other material, it always try to reside on the surface of a conductor. Okay, I'm talking about a conductor. Now, next one, charge density is maximum where the radius of curvature is minimum. Charge density is maximum where the radius of curvature is minimum. If you look here, everywhere the radius of curvature is uniform, so the charge is distributed uniformly on the surface of this body. But when you look at the second body, it doesn't have a uniform curvature. Here the curvature is more, means it has sharp edge near this end and it has wider edge near this end. Okay, so if you take a look here, near this sharp edge, more number of charges accumulated, means the charges prefer to stay where the radius of curvature is minimum. This is the reason the lightning arresters, you know about lightning arresters? Lightning arresters are installed on top of tall buildings to catch the lightning. Okay, suppose there is a lightning means what? Lightning itself is a discharge, no? So suppose you have a tall building over here. On tall buildings these lightning arresters are installed. If you look at the lightning arrestor, it has a sharp edge. Why it has a sharp edge? Because the sharp edges, the charge density is maximum. Okay. So what is this lightning? Lightning itself is a charge, no? So all these charges are grabbed by this sharp edge and is passed on to the ground without causing any damage to the building, isn't it? So the point to remember is the charge density is maximum near the sharp edges, or it is maximum where the radius of curvature is minimum, isn't it? So that is the reason the lightning arresters have sharp edges to grab this lightning and to send it to the earth. Okay, next. More points about charge density. So here there are several types of charge density: linear charge density, surface charge density, and volume charge density. So take a look at linear charge density. The name itself says that when the charge is distributed on the length of any material, here first I have taken a rod and the charge is distributed along the length of this rod. Here on a ring also the charge is distributed along the length of this ring. So whenever charge is distributed along the length, it is called linear charge density. So what is the formula for that? Charge upon length. Okay, so the symbol for charge density is linear charge density is lambda. Lambda is equal to charge upon length. Its SI unit is coulomb per meter. And coming to dimension, we have seen already for charge, we have seen already that is T times A, and since meter is in denominator, L power minus 1. Okay, so the dimension is L to the power minus 1 TA. Okay, this TA is for charge Q. Okay, now what about surface charge density? The symbol for surface charge density is sigma. Surface charge density means charge on a surface. Earlier we have seen it is a length. Now we have a surface of any body, sphere, sheet, any surface we have. If a charge is distributed over the surface of this given material or given body, then we can discuss about Surface charge density. It is represented by symbol sigma. So sigma is equal to charge upon area. Earlier it is charge upon length, now it is charge upon area. And the units are coulomb per meter square. Isn't it? The dimension is meter square means L to the power of -2 and dA is what? Our charge Q. Now moving on to the final one, volume charge density. Now volume charge density means what? Earlier we have seen the charge is distributed along the length and the charge is distributed along the surface. Now the charge is distributed throughout the body, inside and outside. Throughout the body the charge is distributed. So in such case we deal about a volume charge density. The charge is distributed throughout the volume of the material. The charge density is charge upon volume. Coming to units, coulomb per meter cube. And the dimensional formula is, since it is meter cube, L power -3 and TA is what? Our charge. Okay. So these are the basic things to know about before moving on to the actual concepts of electrostatics. And the next one is quantization of charge. Here you see the word quanta. The word quanta means the smallest unit of any physical property. Okay. So here, since we are discussing about charge, what is the smallest charge ever exist in the nature? The smallest charge ever exist in the nature. There are so many subatomic particles. You see, quark, it has a charge of 2/3 times of charge of electron, or sometimes -1/3 times of charge of electron. So these are having the charge less than the charge of electron, but we don't discuss about the quarks now, because we discussed about them in the quantum physics only. Here generally we consider electron as the smallest unit of the charge. Okay. Now see here, the smallest charge that can ever exist in nature is the charge of electron. Generally there are so many other particles which may have smallest charge, but generally we discuss that electron has the smallest charge and we take this as one unit. Okay. If the charge of electron is taken as elementary unit, that is quanta, the charge on any body will be some integral multiple of E. That is, suppose if a body is given 1 electron, its charge is 1e. If it is given 2 electrons, its charge is 2e. If it is given 3 electrons, its charge is 3e. So if you give it 10 electrons, its charge is 10e. Okay. So if you look here, it is an integral multiple of E. It is not 1.1e, it is not 1.5e, it is not like that. It is just a integral multiple. Either it is 1, 2, 3, 4, 5, 6 like that. But never be 1.2e, 3.6e. It won't be like this. Okay. So since it is an integral multiple of E, the formula for charge can be written as a Q equal to plus or minus Ne, where N is the integer and E is the charge of electron, and plus is for positive charge, minus is for negative charge. Okay. Next, charge on a body can never be plus or minus 2/3e or plus or minus 15.6e. It won't be like this. It is always an integral multiple of E. Okay. That is what meant by quantization of charge.